Discrete features. In some applications, we have discrete attributes taking one of n different values. For example, an attribute may be color, which is chosen among the set red, blue, green, black, or another may be pixel, which is chosen among on or off. Let us say xj are binary, Bernoulli, where Pij is defined as the probability such that xj is equals to 1 conditioning on Ci. If xj are independent binary variables, we have that the probability of x conditioning on Ci is equals to the multiplications of Pij to the xj times 1 minus Pij to the 1 minus xj, where the multiplication is taken among all index j starting from 1 to n. This is another example of the Nair-Bayes classifier, where the probability of xj conditioning on Ci are Bernoulli. The discriminant function is g of x equals to log of the probability of x conditioning on Ci plus log of p of Ci, which is equals to, by the definition, is equals to the summations of xj times log ij plus 1 minus xj times log 1 minus pij, xj times log pij plus 1 minus xj times log of 1 minus pij, summing for all index j, then plus log p of Ci, which is linear. The estimator for Pij is Pij hat, which is equals to the summations of xj to the t times ri to the t, summing for index t, divided by the summations of ri to the t, summing for index t. This approach is used in a document categorization, an example of which is classifying news reports into various categories such as politics, sports, fashion, and so forth. In the back of words representation, we choose a priori D words that we believe give information regarding the class. This is from Manning and Schultz at 1999. For example, in news classification, words such as missile, athlete, and culture are useful, rather than ambiguous words such as model or even runway. In this representation, each text is a d-dimensional binary vector where xj is 1 if word j occurs in the document and is 0 otherwise. Note that this representation loses all ordering information of words and hence the name back of words. After training, Pij hat estimates the probability that word j occurs in a document type I. Words whose probabilities are similar for different classes do not convey much information. For them to be useful, we would want the probability to be high for one class or few and low for all others. We are going to talk about this type of feature selection in Chapter 6. Another example application of document categorization is spam filtering, where there are two classes of emails as spam and legitimate. In bioinformatics, two inputs are generally sequences of discrete items, whether base pairs or amino acids. In the general case, instead of binary features, let us say we have the multinomial xj chosen from the set x v1, v2, v3 until vnj. We define new 0, 1 dummy variables as zjk to the t is equals to 1 if xj to the t is equals to vk, and zjk to the t is equals to 0 if otherwise. So let pijk denote the probability that xj belonging to Ci takes value vk. Pijk is defined as the probability of zjk equals to 1 conditioning on Ci, which is equals to the probability of xj is equals to vk conditioning on Ci. If the attributes are independent, we have the probability of x conditioning on Ci, which is equals to the multiplication, the double multiplication, where the outer multiplication is for multiplying all the indexes j starting from 1 to d, The inner one is for multiplying all those indexes k starting from 1 to nj, and with the term pijk to the zjk. Now the discriminant function is then g of x, which is equals to, if we take the log of the previously doubling multiplication, it becomes doubling summation, where the outer summation is summing for all index j, the inner summation is summing for all index k of the following term: zjk times log of pijk, then plus log of p of ci. Now the maximal likelihood estimator for such a pijk is pijk to the head equals to, it's a very common formula that we are familiar with, the summations of zjk to the t times ri to the t, summing for index t, then divided by the summations of ri to the t summing for index t, which can be plugged into equation 5.33 to give us the discriminant.